Psychology tends not to draw a mathematically sophisticated population, and then when we get them in, we don't do a very good job of teaching math. Math is a language, just like any other language, but instead of teaching people to speak it well, what we do with students is give them a guided tour of a phrase book and then boot them out onto the streets of Vienna and hope for the best. So I'll illustrate how I learned the right way to study math. My first statistics class, I became aware that I wasn't really following what we were doing. So I went back and found the first place where I hadn't fully followed what was going on. Here it is, the standard deviation formula. So I spent 4 hours on this formula, and that's what you have to do when you're learning any language, including math. There are certain concepts where you have to pause and thoroughly absorb what that concept is if you want the next 8 or 10 lessons to go in easily. So we'll replicate what I did in a few minutes. So let's take that a piece at a time. What's this part say? Well, it says take each score, square it, and add them up. So I needed some data. So I imagined 3 people who score 2, 3, and 4 on some measure. Okay, I square the scores, add them up, and I get 29. So far, that doesn't make me any smarter, but this formula is supposed to be about how spread out numbers are. So let's compare that to 3 more scores where my 3 people all score exactly the average, no spread. Now when I do this, I get 27. Hey, we may be onto something here. The more spread out group has a higher total when I do this. Okay, let's go the other direction. 1, 3, and 5. Now, when I square and add them up, I get 35. We're definitely onto something here. When we keep the number of subjects and the average the same, the more we spread the group out, the higher this total gets. So I took out some paper and a pencil and I started drawing boxes. So there's the case where everybody scored 3. We square each score and count the number of boxes and we get 27. Okay, now I can see what's going on. When I go to 2, 3, 4, I take away 5 boxes on the left, but I add 7 on the right. That's why the number gets bigger. And then when I go to 1, 3, 5, same thing. I take away 3 on the left, but I add 9 on the right. Okay, I'm getting a feel for how that works. So we've got it saved in a table down there, the 3 groups with the totals of the term sum x squared. Now let's take the next chunk. What is this doing? Okay, well it says add up the scores, square them, and divide by n. Okay, let's do that. Well, no matter which group I'm looking at, when I add the 3 scores, I just get 9. The average is always 3, and there are always 3 scores. So 9 squared is 81, and 81 divided by 3 subjects is 27. Hey, that's exactly the number we got when everyone scored the average. Interesting. Okay, back to the napkin. I draw out 3, 3, and 3, square it, and then divide by 3, and I get 27 boxes. And now I can see that no matter where I put those red lines, 2, 3, 4, 1, 3, 5, I'm always going to get this same result. Okay, so this seems to be just a shorthand way of deriving the total I would have gotten if everyone had scored the average, if there was no spread. So when I subtract this out from the first term, I'm left with just the excess due to how spread out the group is. Okay, so let's put that back. And the rest is easy, so divide by n. So we've got 0 thirds, 2 thirds, 8 thirds, 18 thirds on the bottom line of that table. Okay, so let's review here. We take 2, 3, and 4, we square them, we add them up, and we get 29. Then we add the scores first, square and divide by n to get the total we would have got if everyone scored the mean. And now when we take that away from the first number, we're left with a number that's due to how spread out the group is. I can think of one more test I want to run to see if I'm understanding this. Let's raise the mean. 3, 4, and 5 looks roughly as spread out as 2, 3, and 4 to me. Okay, let's do the same thing. There are the squares, add them up and you get 50. Number's much higher because the average got higher. Now add them, square, and divide by n, and 50 minus 48 is 2, the same number. And just so you know, if you can test it out yourself, if we make the three scores 48, 49, and 50, we still get 2. Okay. So the first term gets us to an excess due to how spread out the group is. The second term adjusts it for how high or low the average is. So we're just left with a number that represents how spread out the group is, regardless of whether the average is 3 or the average is 50. And then when we divide the whole mess by n, we adjust it for having how many subjects. So we could get a higher total just by adding more subjects, but when we do the last divide by n, we get this residue divided up per person. And then we take a square root because we got all this by squaring. Okay, so this number, this formula is really answering a question, sort of, kind of, on average, how far is each person's score from the group average? And when you take the square root, if you look at the bottom line of our little table, 0, 0.8, 1.6, 2.4. If we could go another step, it would be 3.2, 4.0. It's just multiplying each time. Well, now that we understand the standard deviation formula, several more things start to come naturally. Like a t-test is just calculating a standard deviation, but we do it in 2 steps. We separate all our subjects into their 2 groups, and then we get one standard deviation compared to one group, another standard deviation within the second group, and one way of doing it is we'll take an average of those 2 standard deviations. Now we get a second standard deviation using just the 2 group means. Now we can compare the size of that standard deviation to the within group spread, and we can get an idea of how spread out the means are relative to how spread out the groups are. And once you do that, it's easy to add a third group, and now we have ANOVA. Or you can add another factor, a 3 by 2 ANOVA. It's the same concept. We can get within group means, combine them, and then do a standard deviation using the 6 group means. But there's still more. Sum of x over n is how you get an average. This formula is how you get a mean. If you do something similar with cubes, you get skewness. If you do it with the 4th power, you get kurtosis. The bell curve is the only one where all these higher powers are 0. See, you can learn to speak math. Sometimes you need to slow down and absorb a concept until it starts to make sense. But once that happens, you get several more concepts for free. Math is just a language in which the variables are nouns and the operators are verbs. So we can put SAT and GPA on a graph like that, and we can draw a line. When the line is going like this, we're saying X and Y are measured in exactly the same way. Now, if we add or subtract, we're saying the line moves up or down, but it doesn't tilt. The units stay the same size. One scale just starts higher. If we multiply or divide, we're tilting the line. We're saying that the two variables have different sized units. If we multiply one variable by another, we get a curved line. All we're saying is that the size of unit of one variable depends on the number of units of the other variable. And we can go further. When you see pi in an equation, what it usually means is something goes up and down repeatedly, like the tides or the phases of the moon or biorhythms. And when you see E, it says something accumulates, like compound interest, where the more you have, the more rapidly you get more. So you can understand math better than you believe you can. And that's important because science is the search for which verbs capture the way that the nouns of nature influence each other. And math is a language of influence. That's all you can say in math. This course is available from the Great Courses, never pay list price. I bought this, downloaded it, and watched it so that I could be sure that I could recommend it to you. This is the course that explains statistics in English rather than in algebra, so that you'll understand what you're gaining from each step as you learn more and more. So I can recommend that. There are also some popular press books. The one on the left came out in the 1950s. The one in the middle is a really good explanation of how mathematics is not about numbers. It's a rigorous way of thinking about what's going on in the world. And the one on the right, Marilyn Vos-Savant, is a remarkably skilled statistician who has proven the mathematicians wrong more than once. And there are some professional books if you want to learn more about understanding statistics. These two come from APA Press, and they're for the consumer of research, not for the creator of research. John Gottman had to learn time series analysis to study couples, so after he did that, he wrote a book for social scientists. It's an excellent book. And if you want to know more about things like structural equation modeling, this is the book for you. It's a marvelously clear explanation of how those things all work. And there are also some channels on YouTube devoted to teaching statistical methods and concepts. Stand Up Maths is a stand-up comedian who makes mathematical jokes and uses statistics to create somewhat amusing and always educational videos. And there are several others like Numberphile. So, have you ever wondered what's so magical about the bell curve that we use it all the time? Well, around 1815, Carl Gauss was the head of surveying for the Kingdom of Hanover, which is the orange blob here. It's a very messy boundary, and so surveying was rather important. But as he tried to develop the map of the kingdom, he noticed that the numbers he was getting back from his crews didn't lie flat. So he sent out 15 crews to measure the same distance. They got the same first 5 digits on the distance, but the 6th was different. So he marked on a line like this where everybody came down, and he said, aha, that looks familiar. More than 100 years earlier, these two guys, Fermat on the left and Pascal on the right, had gotten involved in helping a rich gambler try to figure out why he kept losing what looked like sure thing bets. And in an exchange of letters, they invented probability theory. So consider a coin. Assume it's a fair coin. If we throw it 1,000,000 times, we expect to see half heads and half tails. If we have two coins and throw them 1,000,000 times, we expect to see 1/4 both heads, 1/4 both tails, and the rest are half and half. What about 3 coins? Well, 3 and 0, 2 and 1, 1 and 2, 0 and 3. 4 coins, 5 coins, 6 coins, 11 coins, 20 coins, 100 coins. You see the shape that's evolving here? And Gauss said, that's what's happening to my surveying crews. Mistakes happen, they're human, but I can make some logical deductions about how those mistakes should work. First off, there's no particular reason a mistake should be too high versus too low. So I can assume that mistakes will be symmetrical around the true values. But I can also presume that small errors are more likely than big ones. But there isn't any size of error in a surveying measurement where I can say it wouldn't get any bigger than that. There's no clear edge effect. So he says, I'm just going to assume there's no edge. The farther you get from the true value, the less likely that error gets, but it never hits 0. And I'm just going to make my life easy by saying if I have 15 measures, the best estimate of the true value is to take an average. But Gauss is a great mathematician, so he didn't say this in English or in German. He said it in math. And there it is. That's the equation for the bell curve. But you can speak math. Pi is about things that go up and down, like phases of the moon. E is about things that accumulate, like compound interest. Sigma is the standard deviation, mu is the mean, and everything else is either your x variable or just a number. And if you look at the bell curve, we have a mean, we have a standard deviation. From left to right, it goes up and down, and from left to right, it accumulates from 0% to 100. Bell curves are a description of a natural process, like the process by which surveying crews make mistakes. They're appropriate when a final score is caused by many different influences that operate on the population, like flipping 100 coins, the different influences, 1,000,000 times, the different subjects. Under those conditions, the best estimate of a population score is the average of the sample scores. And under these conditions, we can calculate just how likely or unlikely any particular score is. And because two bell curves combine to make a third bell curve, we can also figure out how likely or unlikely any combination of scores is. So Gauss says, using this curve, I can look at the scores that my surveyors bring back and decide how likely or unlikely any particular error was, and I can tell whether the crew made a mistake, or whether their equipment needs to be recalibrated, or whether they're either corrupt or incompetent. And it turns out that that set of processes shows up all over the place in nature. This is the return on Standard & Poor's 500 stocks, and this is the distribution of height in the population. So Gaussian curves will show up wherever you have many independent causes adding up independently to create a final score. And even if these are not all fair coins, as long as they're unfair in different directions, you'll get a Gaussian curve. But remember, statistics are how you verify that a certain pattern exists in your observations, and you have to make some assumptions about how those observations are working in order to pick a statistic. What if your assumptions are wrong? Well, this coin is a Belgian euro. The Belgians chose King Albert for the head of their euro, and he was a fairly large gentleman, such that a Belgian euro is not a fair coin. It comes up tails 2/3 of the time. So if we repeat our experiment and throw 100 Belgian euros a million times, we're not going to get a bell curve. We're going to get a skewed curve. Now, I'm sure you've seen many times in psychological studies where the researchers said the fact that we got a skewed distribution on this variable is highly significant, and the skew itself is telling us something important about nature, right? No. They take a square root and then pretend it never happened. They just made the effect go away. Skewness is telling you something non-Gaussian is going on, and you should go look for it. In fact, I hope you noticed this curve is not a bell curve. It's kurtotic. It's too tall in the middle and on the tails, and too low in the shoulders. Okay, so we're scientists. We can make a guess as to why that's a non-Gaussian curve. I have two thoughts. First off, most of the time, if a stock goes up a little ways, somebody's going to sell it and take their profit, and that pushes it back to the middle. Or if it goes down, somebody says, now it's worth buying, purchases it, and pushes it back into the middle. But a few stocks make big moves, and then people pile on. So we thin out the shoulders and move stocks mostly into the center, but also into the tails. Now that's a guess. We would want to test that out. But that's how you can analyze non-Gaussian distribution and use it as a way of generating hypotheses that you can test. So let's do some thinking about our reality. So does intelligence follow a Gaussian distribution? Well, are there many different factors, each of them affecting your final intelligence, acquired independently, that affect intelligence like tossing 100 coins a million times? I'm going to say, yeah, that looks plausible. I mean, we don't know that that's true, but it makes sense. That means intelligence can plausibly be modeled using a bell curve. So when the IQ test people force the data into a bell curve, at least it's reasonable. Or we can look at it the other way. Are the underlying causes of intelligence just as likely to be high as low, or are they biased toward one extreme? Are smaller moves more likely than bigger moves? And are there no clear edge effects beyond which you can't get smarter or dumber than that? Again, that all looks plausible. So again, intelligence is reasonable to model using a bell curve. What about depression? Let's look at Gauss's factors. Are the underlying causes biased, or are they just as likely to be high or low? Well, they're biased because most people aren't depressed. Are smaller variations more likely than big ones? I don't even have a good guess. Are there no clear edge effects? Well, yes, there's a clear edge effect. It comes where there's zero depression. It doesn't make sense to talk about a negative depression score. So a bell curve is not appropriate for modeling depression. This is a Gompertz curve. Instead of a mean and a standard deviation, we have an eta and a b. You don't need to worry about what those mean right now. The main differences are this curve is not symmetrical and it has a hard zero. And this curve can be analyzed just as well as a Gaussian. So in fact, here's an article I found, a prognosis calculator for major depressive episodes using episode duration to predict how long it's going to last. And lo and behold, these people found that a Weibull distribution is the best fit to the data. When you see people using a distribution other than Gaussian because they tested it, you're looking at a very good set of researchers. Those are people you can trust. You don't need to understand what a Weibull distribution is to look at this article and say, this calculator is probably a good one to use. I can use that in my clinic.